Okay, works. Okay, now next. On. Reason, huh? Okay, thanks. Nice to see everything's good. Okay, can someone speak on the other end who's online, please?
Morning.
Great. One more time, please.
Good morning.
Great. All right, we can hear you very well, thanks.
You're welcome.
Can you hear me okay?
Yep.
Yeah, I can hear you fine.
Great.
Yes.
Okay. All right, so maybe we should start class. So I received the homework scores back. You should be able to look at your homework on OneNote. So your scores should be recorded on OneNote. Your homework should be graded from homework 1. Let me just put these on. Let me just write these down. So homework 1 is now graded and is now available for you to look at. Okay. All right. Now for homework 2, I know it was sort of the Labor Day weekend, and so the homework 2 you should turn in by the end of the day tomorrow. So homework 2, and I'll let the grader know it's due end of the day on Thursday. Okay. All right. The third announcement is we're completely caught up in terms of notes and videos. So if you want a complete up-to-date set of notes for the class, they're posted on ELC under content. Okay, so you can actually go to ELC and find the notes for the class. And then the videos for the class are all posted on the YouTube channel that I have. So the videos are all posted on YouTube. And I gave you the link beforehand in the email. Okay, any questions on this? No? Good. I was very pleased with the homework overall. I mean, everyone did. I mean, as a class, you guys did very well. So I was very, very pleased with that. Okay, so we're going to go back and I'll review a little bit. It's been a while. And what we'll do is we'll talk about linear independence. So the idea with linear independence is we have a set of vectors and we want to actually make sure they're not redundant, which means that one vector cannot be written as a linear combination of the others. So let me draw you some pictures just as a review. So let's say this is the XY plane, XYZ plane. And let's say I have a plane like this. Okay. And let's say I have some vectors here. Let's make them some colors. Let's do some blue. So if I have three vectors in the plane, V1, V2, let's say V3. So let's say they're all in the plane here. So V1, V2, and V3 are contained inside the plane P. Well, then V1 is a linear combination of V2 and V3, and the other ones are the other two also. So this set is not linearly independent. Okay. Now, on the other hand, what I can do is I can take a set of vectors in 3 space again, and let's say the vectors are not in the same plane. Okay? So if I take this vector here, V1, let's say V2 goes in this direction over here, and let's say V3 goes out in this direction. Okay, so no vector is in the plane generated by the other two. So then V1, V2, and V3 are linearly independent. All right, so now how do we make this precise? So I gave you a definition last time. So let's recall the definition. So a set of vectors V1, V2, up to Vt, let's say in Rn, okay, is linearly independent. Okay. If and only if, whenever I have a linear combination of vectors equal to the 0 vector. So whenever I have a linear combination equal to the 0 vector, then the coefficients all have to be 0. Okay, so what it says is that I cannot express the 0 vector as a linear combination, a non-trivial linear combination of these vectors. All right, now when we look at this, we've kind of seen this before. So what we can do is we can sort of think of this as a linear system and sort of translate what it means to be linearly independent to linear systems. So let me also remark and make the following remark. So if a set of vectors are not linearly independent, then they are what's called linearly dependent. Okay. So not linearly independent means linearly dependent. Okay, any questions on this so far? Okay, so so now let me take this equation star and let's translate it into the language of systems of equations. So let's look at systems of equations again. And so what I'm going to do is I'm going to make my matrix A appear. And what I'll do is I'll put the vectors down the columns. So V1 is the vector, and I just put it down the column. V2, I put down the column. VT, I put down the column. Okay? And my vector C will just be the coefficient C1, C2, up to CT. So when I write star out, so star is precisely AC being the zero vector. Okay, so the equation star is just in terms of a more compact notation, it's just AC being zero. So we've seen this before. This is a homogeneous system. So now I can just say that the vectors are linearly independent if and only if the homogeneous system has only the trivial solution. So consequently, the vectors V1 up to Vt are linearly independent if and only if the only solution to AC equals 0 is the solution C equals 0. Okay, so as long as you put the vectors down the columns of the matrix, you look at the homogeneous system of equations, if it only has a zero solution, has a solution. I mean, if it has free variables, then all bets are off, right? But if there are no free variables and you have only the zero solution, then the vectors are linearly independent. Okay, any questions on this? We're going to do some examples in a moment. Questions? All right, so let's put this into practice. So let's do an example here. So determine if the vectors 3, 0, 0, minus 3, 2, and 3, and let's see, 6, 4, 1. Ooh, that is a 6. 4, 1. Okay, are linearly independent. Okay, so that's the problem. Okay, so how do we do this? Anyone?
We would put the vectors in a matrix
Yes?
called A, and we would augment that with the zeros and see if if there's any free variables. If there isn't, and the only solution is that, then it would be the linearly independent.
That's right, exactly. So we need to consider, whoops, sorry about that. So we need to consider AC being 0. Okay, and A here is the matrix. I'll even write it out the first time. Okay, 3, 0, 0, minus 3, 2, 3, and 6, 4, and 1. Okay, so we need to look at this homogeneous system. Ooh. All right. Okay. All right, let me kind of. Okay, that was so pretty. Okay. All right, so now I'm going to look at this homogeneous system, and I'm going to see if it only has a trivial solution. All right, so as you mentioned, I'm just following your directions. 3 minus 3, 6. I'll put a 0 here. 0, 2, 4, 0, 3, 1. And we look at the homogeneous system like that. Okay? All right, so let's do this. Okay, so I'm going to multiply. So you already have zeros down the first column, okay? So I don't have to worry about using the 3 to knock things out. So I'm going to knock out the 3 over here. I'm going to multiply the second row by, let's say, 3, and then the third row by minus 2. Okay, so again, it's 3 times row 2 plus minus 2 times row 3. And I'm going to put the answer in row 3. There. Okay, so let's do this Gaussian elimination. 3 minus 3, 6, 0. Okay, 0, 2, 4, 0, 0. Okay, so 3 times 2 times 3 times minus 2 is 0. 4 times 3 is 12. Minus 2 is 10. And then rows have a 0. Okay. Conclusion?
Linearly independent.
So this is linearly independent. Now, if you want to back substitute up, then you can see that if I have all these pivots being here. So for example, I have 10x or 10c3 being 0, right? So that means c3 is 0. I back substitute up 2c2 plus 4c3, which is 2c2, that's 0. So that means that c2 is 0. And then finally, 3c1 minus 3c2 plus 6c3 has to be 0. We know this one's 0. We know this one's 0 too. So that means that 3c1 has to be 0. That means c1 has to be 0. Okay, so when we have all the pivots there and no free variables, then the only solution to the homogeneous system is actually the trivial solution. Okay. Any questions? All right, so let me do another example. Okay. So let B1 equals 1 3 minus 2, B2 to be equal to 2 minus 6, 4. Okay. And finally, B3, these are all vectors, so I'm going to put vector signs at the top, is that's 1, 2, and a variable h. Okay. So the question is, for which h are these vectors linearly dependent? So for which h are the vectors v1, v2, and v3 linearly dependent? Okay. All right, so we just proceed like we did in the last problem. We set up the homogeneous system, and we do Gaussian elimination, and then we sort of figure out whether we have free variables or not. Okay, so let's set up the Gaussian elimination. Okay, so we have 1, 3, minus 2, 2, minus 6, 4, 1, 2, h. What did I put in the last column? What goes in the last column over here? All zero. Zero. Question? Okay. So again, this represents AC being 0. Okay, so we're looking at the homogeneous system. We're going to try to see whether C is actually 0. Okay, so let's run Gaussian elimination. Okay, so I multiply the first row by minus 3, add it to the second row, and put the result in the second row. So 1, 2, 1. I have a 0 here. I have a 0. Let's see, what's next? Interesting. Minus 3. Okay, so what do I get? Do I get minus 12? All right. Yes or no? Oh, sorry. I apologize. There's one. I made a mistake on this problem. So this should be a minus 2. I'm sorry. Let me put a minus 2 up here. Okay, so this should be a minus 2. I apologize. All right, now it's going to work out the way I wanted to. Okay, so I just changed this to minus 2. Okay, so now let's do this. So I have minus 3, minus 2, multiplied them together, I get 6, plus minus 6, I get 0. And then I get minus 3, plus 2, that's a minus 1. I get 0. Okay, is everyone all right with that? Okay, good. All right, now I'm going to get rid of the minus 2, so I'm just going to multiply the first row by 2, add it to the third row, and then put the result in the third row. Okay, so I get a 0 here, and then what do I get? What's the next term going to be? Anyone?
0.
0. Okay. The next term is going to be h plus 2. And the next term is 0. Okay, so we're not quite done yet. Can anyone tell me what's going to happen right now?
There's a free variable.
Yeah, there's going to be a free variable. And so I can eliminate the last one by just multiplying the whole thing by h plus 2 onto the second row and then adding it to the third row. Okay, so then I get 0, 0, 0, 0. Okay. All right, so as you can see, the pivots are here and here. And so I have a free variable. So I'm going to have non-trivial solutions. So there's a free variable. So namely, guess C2 equals T. So there are infinitely many solutions. Okay, so you just don't have the zero solution. So these vectors are always linearly dependent. So V1, V2, and V3 are always, oh, what's this? Sorry, I did something weird. Let's see this. Okay, always linearly. Guess you got to see my favorite baseball team.
And on this Roberto Clemente day, let's just take a closer look.
Wow.
Class of 73 with a batted title a bunch, 12-time Gold Glove winner, great defender, MVP back in 1966,
Ooh.
29 home runs, 119 RBIs, a superstar athlete and person.
Okay, let me get rid of. Okay, you can see who my favorite baseball team is. Okay, great. A little bit on the side. Okay. All right, so are there any questions on this? So again, let me kind of recap. We took three vectors over here. We want to know when they're linearly dependent. So for which H they are. We use Gaussian elimination to actually figure this out by looking at the homogeneous system. We saw that there was a free variable, so there are infinitely many solutions. So the vectors are always linearly independent. And it doesn't depend on what H is. Okay. So it doesn't depend on H. Okay. Any questions? That was an interesting detour to solving this problem. Okay. All right, so now what I want to do is I'm going to show you that if you have linearly dependent vectors, then one vector is going to be in the span of the others. So let's actually prove that. So here's the theorem. So suppose that V1, V2, up to Vt are linearly dependent. Okay? So then, at least one vector is a linear combination of the others. Okay, so let's see why this is true. All right, so here's a justification. So if you like to call it a proof, I actually like better, proof is kind of a scary word. So let's just see why we think this is true. So we just, I mean, it's better to just sort of think about why instead of like, oh, it has to be true. All right. So if the vectors are linearly dependent, so V1 up to Vt, linearly dependent means that I have a linear combination V1, C1, V1 plus C2, V2 plus CT, VT, which is the zero vector where Cj is not equal to 0 for some j. Okay, so we can write the zero vector as a linear combination of the other vectors where one of the coefficients are not equal to 0. Okay, so then what we do is we just take that vector Vj, stick it on one side, move everything else to the other side, and then divide. Okay, so that means, so if I take Cj, Vj, that's minus C1, V1, minus C2, V2, and then we're missing the Cj, Vj term. So I'm going to put a hat over this, meaning we don't include it, okay? Dot, 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 minus CT, VT. Okay, so basically you move everything over other than the term Cj, Vj. And since Cj is not equal to 0, we can just divide. So Vj is going to be equal to minus C1 over Cj, V1 minus C2 over Cj, V2, minus CT over Cj, V2. So what this says is that the vector Vj is a linear combination of the other ones. Okay? So Vj is a linear combination of the other vectors. All right. Now, when we're done with the justification, we often put the tombstone down. That box is what we often refer to as the tombstone. Okay, any questions? Another way to say it is QED if you want to say it that way. Okay, any questions on this? All right, so now what I'm going to do is I'm going to take some vectors and we'll actually write one of them as a linear combination of the others. Okay, so let me look at the next example. So let V1 to be equal to 1 minus 5. V2 to be equal to the vector 4, 7. And V3 to be equal to vector 2, 0. Okay. So there are two parts of this problem. So part 1 is show the vectors V1, V2, and V3 are linearly dependent. Okay, so we kind of know how to do this using AC equals 0. And then the second part of the problem is to express one vector as a linear combination of the others. Okay? Okay, good. Any questions on this? All right, so let's do the first part. So the first part, for 1, we're looking at, again, the homogeneous system of equations. And in order to analyze that, we just set it up as we normally would. Okay, everyone all right with that? Okay, AC equals 0. All right, so there's not much we have to do, right? We just have to knock out the -5, and then we'll see what happens. Okay, so I multiply the top by 5 here. And then what do we get? We get 1, 4, 2, 0. The next one's a 0. What's the next one after that? Let me make sure I'm not making any mistakes now. So this should be all right. Okay, this looks correct. Okay, so what's the next term then?
27.
27. And the next term is?
10.
Okay, and then we have a 0. Okay, so it's a little bit more complicated, but that's okay. We can deal with it. All right, so where are the pivots? The pivots are here and here, right? So what's the free variable? X3, right? So this is free. Okay, so we have a free variable. So what does that say about linear independence or linear dependence? Are they linearly independent or linearly dependent?
Linearly dependent.
Linearly dependent, good. So this implies infinitely many solutions. So V1, V2, V3 are linearly, actually this should be, let's call it C3, okay? Linearly dependent. Well, let me clean it up a little bit. Clean this up a little bit. Okay, any questions on the first part? All right, so now what do we have to do next? We have to express one vector as a linear combination of the others. So remember, what we're trying to solve here for 2, what we have is we have C1 V1 plus C2 V2 plus C3 V3 is equal to 0. So in order to write one as a linear combination of the others, we have to find a solution, a non-trivial solution, and that will be good enough. And then we just move everything to the other side. So the goal is to find non-trivial solution. And we only need one. We don't need to find them all in some sense. Maybe we will find them all. Okay, so in order to do that, let's back substitute. So remember C3 is T, which is free. Okay, so now let's back substitute. So 27 C2 plus 10 C3 is 0. Okay, so that means 27 C2 plus 10T is 0, right? So that means, let me just save some space. So what is C2 going to be? C2 is going to be minus 10 over 27T, right? Everybody okay with that? That looks pretty good. Okay, so we have C3 being T here, C2 being this. Okay, and now we can back substitute up one more time. So we have C1 plus 4C2 plus 2C3 being 0. Okay, that's the top equation up here. Okay, so that means that C1 plus 4C2, so that's minus 40 over 27T, okay, plus 2T is 0. Okay, so that's C1 plus minus 40 over 27T plus 54 over 27T equals 0. Is that all right with that? 54 over 27 is 2. And then it's not so bad. So C1 plus 14 over 27T is 0. So then C1 is equal to minus 14 over 27. Okay, so if we want to write out the general solution, we can. C1, C2, and C3 is going to be equal to minus 14 over 27. And C2 is minus 10 over 27. And C3 is 1. And I multiply that. Okay, everybody all right with that so far? Actually, before I do this, let me clean it up slightly. Okay, so let me write this in a little bit better. That's a 14. Okay, so like I said, we only need to find one solution. So why don't we set t equal to 27 so that we don't have to deal with a bunch of fractions. Okay? So now we set, let's say t equal to 27. So then in that case, I have C2, 1, C2, and C3. And what am I going to get here? I'm going to get minus 14, minus 10, and 1. Okay? So we know that minus 14 times V1 minus 10 times V2 plus V3 is 0.
Wouldn't it be 27 instead of 1?
27, thank you. Thank you, that's right, 27. Okay. That's the advantage with this, is I can erase. So, plus 27. All right, does that look good? Look better? Multiply by 27, okay, good. All right, so now we're in business, right? We can just take any one of them and write it as a linear combination of the other two. So let's just take let's take V1 for example. So that means that minus 14 V1 is equal to 10 V2 minus 27 V3. Okay, and then I just divide by 14. So V1 is equal to minus 10 over 14 V2 minus 27 over 14. That's plus V3. Okay, so I've written one of the vectors as a linear combination of the other. Oops. Okay, any questions on this? Yeah, this was the goal for part 2, right? Sorry. Yeah, part 1 was to show they're linearly dependent. Okay, part 2 was to express one vector as a linear combination of the other two. So to solve part 2, we had to find a particular solution. And once we found a particular solution, that allowed us to sort of take one of them and then sort of move the other ones the other side and just divide. Okay? All right, good. All right, so let me make an observation. I mean, this is maybe you've seen this already, but let's make a little bit of an observation. Okay, so let's call an observation. All right, so let's look at the vectors. So we have vectors v1, v2, up to vt. And let's say they're in Rn. All right. So what I want to do is I want to look at the matrix here. So when I look at the matrix A, I stick V1 here. I have V2 over here. And I have VT. Okay. What is the size of this matrix? How many rows and how many columns are there? Anyone? Well, first of all, how many columns are there?
T columns and 3 rows.
Right. So there are T columns. Okay, so this is in Rn.
Oh, RN, sorry, I thought that was a 3. N rows. Or-
N rows, very good. All right. So there are N rows. So there are N rows here, and then there are T columns. All right. Now let's just use our imagination. So can anyone tell me like when you're going to have free variables? When there are more, right? So if T is bigger than N, there has to be a free variable. Okay. So AX or AC equals 0 has a non-trivial solution. Okay. I.e., the columns of A are linearly independent or dependent.
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 Okay. All right, so that's the theorem. So the theorem is that V1, V2 up to Vt, the vectors in Rn. If the number of vectors is bigger than n, then this set is linearly dependent. Okay. All right. So let's just kind of frame this down the road. So let me just do an example really quick. So let's say I have R2, right? And let's say I have 15 vectors in R2. All right. So then they have to be linearly dependent. So 15, say, non-zero vectors. In R2. I'm assuming they're distinct too. Are linearly dependent. Okay, so this kind of makes sense in terms of your intuition. If I have 4 vectors in 3 space, they have to be linearly dependent. If I have 5 vectors in 3 space, they have to be linearly dependent. If I have 4 vectors in 4 space, then I don't know. Maybe they are, maybe they're not. Okay. Okay. So let's see. Let me give you another example here. Here's a quick example. Let A be a 7 by 5 matrix. Okay. How many pivots must there be for the columns of A for the column to be linearly independent? Okay. All right. So, you can imagine doing Gauss elimination on this. So here's your matrix A here. And there are 7 rows here. Erase this thing. I write it needed. Getting too excited. There's 7 rows and there are 5 columns. Okay. All right. So how many pivots are we going to need in order for this to be linearly independent? Columns.
5.
5, right. So basically, we're going to have 5. I should have drawn it a little bit better. So we actually need to have a pivot in every single column. So we have to have 5 of them in order to have the columns be linear. So the answer is 5. Okay, so with 5 pivots, that means that there's no room for free variables. With no free variables, then we can say that only the 0 solution is the only solution to the homogeneous system. Okay, any questions on this? Questions? Okay, so let me stop here. Next time we'll talk about linear transformations.
Thank you.
Dr. O'Connell, I have a question.
Yes?
From the homework 1,
Yeah.
one of the problems, we had 2 free variables, and I set them both equal to t. Is that not correct? Like, I thought we always set free variables equal to t.
No, if you have 2 free variables, you have to set them equal to different things. So one of them you should set equal to s, the other one you should set equal to t.
Okay. All right,
Okay.
thank you.
Okay, good.